Hello again. This is Math 1120 coming to you from the College page, and this is a discussion of the low-stakes assessment entitled Skewness and Normality Considerations. By way of introduction, relative to skewness, we can sometimes eyeball data and determine how and if it is skewed. If we have a picture to look at. If we do not have a picture, we should make one, maybe multiple pictures. There are also many numerical measures to help us figure out how skewed is the data. We're only going to discuss two of them here in these notes. And relative to normality, it is often important to discern if a population is normally distributed, and we usually do this by extracting a random sample and see what the random sample tells us about if the population is normally distributed or not. Again, pictures can provide insights, box plots, histograms, so on and so forth. Also, there are quantitative tests that can be applied. We will discuss one here, but there are much fancier tests that are available to test such things. Relative to skewness, Pearson, the same Pearson that we talked about in linear correlation, developed coefficients of skewness. The first one was the mean minus the mode divided by the standard deviation. But you don't always have a mode, and so a second skewness coefficient that's maybe a more popular one back in the day was 3 times the mean minus the median, all divided by the standard deviation. And this is a simple multiple of a non-parametric skew that doesn't matter to you probably. And Pearson did much more with this. He was a heavy-duty researcher. But here are the pictures that he based these ideas on, and here are some of the conclusions about the positive, negative, right or left skewness of something. But many textbooks teach this as a rule for skewness, but this rule can fail with surprising frequency, and they talk about ways that it can fail. But I will also tell you that in my decades of experience, however, these anomalies tend to be mathematical and somewhat contrived situations, rarely occurring in practice. The counterexamples are important to the theory and research progress, but will not be observed in the real world. As you might expect, there's a function in Excel that does this. Here's the formula function in Excel. The skewness is equal to n divided by, and I really think this formula is written in a way I don't like it. It's n divided by, this whole thing is the denominator here, n minus 1 times n minus 2. But then you take that business times the summation, and each of these terms is xi minus x bar divided by s whole cubed, and then you add them up. And here are what all those variables mean. And, of course, there is the Excel function here. Now, normal probability plots, we're going to discuss those, and those are really a powerful way of doing this, but those involve very significant calculations. And this is a nice paper from Penn State I wish we had time to talk about, but alas, we have limited time for such work in our current course. Beyond a rudimentary discussion of normal probability plots, more on this soon in class. So, let's turn to the assessment then. I am giving you a data set. It is called SN Data in Blackboard, the syllabus tab. I'm asking you to draw a histogram. What does this tell you about the skewness? What does this tell you about whether this sample came from a normal distribution or not? Draw a box plot. What does this box plot tell you about the skewness? What does this box plot tell you about whether this came from a normal distribution or not? Use the Pearson second coefficient for skewness to find the value. What does this tell you about the skewness? And what does this tell you about whether this came from a normal distribution or not? Then I'm asking you to do this twice in Excel. First, using the Excel formula itself. I corrected that, remember. And the second thing is using a built-in Excel function. And you, by the way, should get the same answer on both of those. Number 6, use the data to test the fit of the data with the empirical rule for normal distributions. What would this lead you to conclude about whether the sample came from a normal distribution or not? Explain your answer. In summary, what do these calculations and observations tell you about whether the sample came from a normal distribution or not? In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.